Hello. In this video, we continue to look at a multiple regression model, and we will do some further analysis on multiple regression. So we have here our multiple regression model in this format right here. And so here we will base ourselves on one example, this one right here. Okay, so I'll use this example with two independent variables, x1, x2, to explain or predict annual restaurant incomes. Okay, this is an Excel output, and so here we are. We have all the information we need for the next hypothesis test, in fact. Okay, so we saw in the previous video how the coefficient of determination r squared and the adjusted coefficient of determination, so the r square with a bar on top, right? That's this value right here, okay, which we find in the Excel output to be this right here. So we found how these two measures here can be used to assess how the multiple regression model is efficient in explaining or predicting the total variation in all observed values of y. Now we turn to another method of getting that same information. We want to now test the relationship between the overall regression and y, this time using the F distribution. Okay, so we will conduct an F test over here. The idea over here is that in our null hypothesis, we state that none of the independent variables are significantly related, I should say, significantly related to y. So when we say the independent variables, we also talk about the slopes associated to each independent variable. So if you've got k independent variables, you've got k slopes, hence k betas, yes. So the idea is to say that all the slopes are equal to 0 in the null hypothesis, versus the alternative is saying that there is at least one slope that is non-zero. And hence there's at least one independent variable, x here, x of j, that is significantly related to y. Notice here that this is a one-tailed test. Okay, even though it might not look like a one-tailed test in the alternative hypothesis, it actually is a one-tailed test. Okay, so if we're going to use the F distribution over here and come up with a F test statistic over here to compare it to a critical value, we need to make sure that the four model assumptions on the error terms hold. So that is the basis for doing this testing, and for all hypothesis testing actually moving forward in multiple regression analysis. Okay, so the test statistic here is determined by taking a ratio of your explained variation to the unexplained variation. And so to do that, we take the explained variation, that's your SSR, and we divide it by here a factor of k. K, once again, is the number of independent variables, or yes, number of independent variables that you have in your regression model. In this case, if I'm referring to the restaurant example with x1 and x2 as being my independent variables right here, then I see that I've got two independent variables, right? So I would be dividing my SSR, that's my explained variation, by 2. That's for the numerator. In the denominator here, I'm looking at my unexplained variation. That's the SSE, the sum of the squared residuals, for the unexplained component. And that is divided here by n minus k minus 1. Okay, so if I've got 10 observations in my sample, and I'm using two independent variables, x1 and x2, here in this denominator part overall, I'm dividing my SSE by 10 minus 2 minus 1. The minus 1 is to make up for that beta naught point estimate that I must use as well in my multiple regression model. Okay, so actually, when you look at the Excel output, you can actually find the F value. The F statistic value is actually given right here. Let me just enlarge it right here. So you see that you've got here 180.689. That is my test statistic as a result of actually taking this value right here divided by that value right here. Okay, and further, Excel gives me the p-value equivalent to that test statistic. So I can see here that my p-value is extremely small, pretty much equal to 0, almost. Okay, so I'm going to compare that test statistic, of course, to a critical F value. How do I compute my critical F value, or how do I determine it actually? Well, here I need to know what my level of significance for the hypothesis test is. Here that is alpha. So if my alpha is at 0.05, then that's the alpha I'm going to use, which means that I'm going to be using an F table for a right tail area of 0.05. Okay, because remember that the F distribution, there is one different F distribution for each, over here, there is one F table, I should say, for each alpha that is being used, right? Okay, further here, degrees of freedom 1, well, that's the degrees of freedom in my numerator. Degrees of freedom in my numerator is actually K. So that would be 2. Degrees of freedom 2, that's my second set of degrees of freedom. That's coming from my denominator. So here I've got, 10 minus 2 minus 1 is 7, right? So I've got to find my critical value for an alpha of 0.05, a df1 equal to 2, and a df2 equal to 7. So let's just quickly do that exercise. Let's go look at the F table. So again, I want to make sure that I'm using the right F table, because you'll notice in your textbooks that there is one table for each right tail area. So make sure you're using the correct right tail area. Here I'm using 0.05. And so I want my df1 to be equal to 2, and I want my df2 to be equal to 7. Hence, I get this F point right here. That's my critical point of 4.74. Okay, so really what I'm going to do now in my decision rule is compare my F test statistic, which I found to be 180, relative to my critical F point, which turns out to be 4.74. So clearly the decision here is that you reject the null hypothesis, which is of course stating that there is no relationship between the independent variables and y, right? So you reject the null hypothesis over here if indeed your test statistic is greater than your critical value. Okay, so we can see clearly that is the case over here. Hence, I can say that my multiple regression model does explain why to some extent, right? Okay. Then if I am to use the p-value approach, so that can also be an option, the p-value approach, well, the idea over here is that you want to find an F point of a value that is of 180, a value that is greater than my test statistic, F. Okay, so I found my test statistic to be equal to 180.689. So I want to know what is the likelihood of finding an F point that is greater than 180.689 for a fixed set of degrees of freedom. Here df of 1 equals k. In this case, I'm looking at 2, and df of 2 equals n minus k minus 1. In this case, I'm looking at 7, right? And of course, the p-value is always assuming that the null hypothesis is true, right? So if the null hypothesis right here is true, what is the likelihood of finding an f point of 180.689 or more for this set of degrees of freedom, right? So the way to go about this, I'm just going to do a little dry run with you here on this one. Let's go here. So here I've got my first F table. What I do is I start by looking at my first F table over here. Okay, the first one that shows up is for a right tail area of 0.1. In other words, 10%. That's my right tail area. And what I want to do is for the fixed df1 equal 2 and fixed df2 equals 7, I'd like to know what is that f point. That f point here is 3.26. I've got the objective here is to find an f point that is greater than 180.689, which was the value I found for my test statistic. So I need to go through all F tables until I find the one F table that gives me a right tail area that is that seems to make sense. That has an F point close to my test statistic. Okay, so 3.26 is clearly too small. It's really not close to the 180. So I move on to another F table. The next one gives me a right tail area of 0.05. That's the tail area right here. And so now again, I'm going to go find my F point for df1 is 2 and df2 is 7. Here I find 4.74, clearly not close to the 180 and some odd. So I continue to look further on the right in my F distribution. I'm going further right. So my tail areas are getting smaller. Okay, here we are. I now get to this tail area of 0.025, and for df1 of 2 and a df2 of 7, I'm not, I mean, my f point is increasing, but it's still not close to the 180. So I continue searching until I can no longer search. So here we are. This is, well, actually my last F table that I have here for a right tail area of 0.01. In other words, I'm looking at a tail area of 1%. And I see here that when I cross df1 equals 2 and df2 equals 7, I've got here an F point of 9.55. So what can I conclude? Well, I can conclude here that my p-value is going to be very small and very close to 0. Okay, that is using the table approach, right? Now, if you look at the computer output, so here if I look at my Excel output, well, I have my p-value. It's given to me. I don't need to do that search in the tables, in the F distribution tables. So this computer output here tells me basically that my p-value is very, very small. The rule here, the decision rule using the p-value approach, states that you reject the null hypothesis if your p-value is less than your level of significance. So my level of significance here is 0.05. If it is 0.05 and my p-value is very close to 0, then clearly this condition here has been met. And so over here, I conclude that I must reject the null hypothesis. So once again, you know, the conclusions concord, right? They are both the same. And that is always the way it works, right? Whether you use the critical value approach to come up with a decision rule or the p-value approach, your conclusion must always be the same. Okay, so that is the F test. Okay. Now there is also a second test that we can use, and that is to test the significance of a single independent variable x of j at a time. Okay, so in this case here, I just want to look at the individual independent variables. Say I'm only interested in knowing whether or not x2 is significant in explaining why, right? So what I do here is I will use the t-test, okay? So let's just go here. So here the idea is that my null hypothesis states once again that for the independent variable that I am interested in testing out here, I will look at its slope. Okay, so I say here beta of j is equal to 0. In other words, here there is no relationship between y and x of j. That's what it's stating pretty much. Versus the alternative is saying that beta j is different than 0. Okay, so the way now it is set up is that I have a two-sided test. Okay, mind you though, this can also work for a one-sided test, depending on what you're being asked. But if I am simply testing for the significance of an independent variable and not testing for anything else, like say if the slope is positive or negative, say, so if I'm simply testing if an independent variable is significant or not, then this is the format to use right here. And so it is a two-sided test. So here I use the t-test. My test statistic will look like this over here. So I am comparing basically my point estimate for the regression parameter beta j. The point estimate here comes from the method of least squares, of course. And I subtract the population parameter estimate over the population regression value here, regression parameter value, which should be 0. And I divide that by the standard error for my sample bj, my sample estimated b of j. Okay, so that will be compared to a critical value t of alpha over 2. Why alpha over 2? Well, because it is a two-sided test, right? And so I must divide my alpha, my level of significance, by 2. And also for a known degrees of freedom, now be careful over here, the degrees of freedom that you will use over here is d of f equals n minus k minus 1. And this is true for any and all beta j's when conducting the t-test. Okay, so you must always use degrees of freedom here, n minus k minus 1. It doesn't matter if I'm testing for the independent, for the variable, yes, the independent variable x2 or x1 or x10. Degrees of freedom here must always remain of this form right here, n minus k minus 1. Okay, so the decision rule over here is that you will reject your null hypothesis if your test statistic right here is greater than your critical statistic. Okay, so let's quickly go look over here at our Excel output to see what we're actually getting for the test statistic. So you will get the test statistic value in your output, right? It is given to you. So for instance, for independent variable x2, which is business rating over here, I see that I get a t-test value of 3.95, okay? And so I need to compare that, of course, to a critical t-value. The critical t-value here, if I'm using a level of significance of 0.05, sorry, 0.05, then let's just go look quickly and see what we can get as a critical t-value. Here we are. So if my level of significance is of 0.05, this means that I'm going to look at an alpha over 2 for a two-sided test. Okay, so I'm looking at alpha over 2, which is t of 0.025. My degrees of freedom here will be equal to 7. And so I see that I'm getting this t point. This is my critical point of 2.365. So remember that, 2.365. Now if I go back to my decision rule, so here I see that I had a t-test value of 3.95, which I got from my Excel output, and I'm comparing that to a value of 2.365, I think that was the number, yes. And so clearly here, my t-test value is greater than my critical point, hence I reject the null hypothesis. Okay, now if I am to use the p-value approach, well, here you have to be careful, because if it's a two-sided test to begin with, the p-value here will now be equal to 2 times the probability of finding a t-point that is greater than the t-test value for a fixed degrees of freedom of n minus k minus 1. Okay? Of course, always under the assumption that the null hypothesis is true. So you have to be careful here not to forget to multiply this probability right here by 2. This is only when you are using or conducting a two-sided hypothesis test. If my hypothesis test is one-sided, then the p-value does not have to be 2 times this probability right here, but rather the p-value will simply be equal to the probability of finding a t-point that is greater than the test statistic value, right? So please keep that in mind. Okay, so let's just do a little exercise once again. Let's go find this p-value over here. So we have a test statistic, let's not forget, of 3.95. So I'm going to go look over here for 7 degrees of freedom. Remember, I have to identify at the beginning what my degrees of freedom is when finding my p-value, right? That's an important step to do. So here I know I'm using 7 degrees of freedom. So I look in my row of 7 degrees of freedom, and I'm going to have to find here a t-point that is greater than 3.95. That's my t-test value. So I see here that, I've got a t-point of 3.499 and another t-point of 4.785, which tells me that the t-point that I'm looking for is somewhere in between these two t-points, which tells me that my p-value will lie somewhere between 0.001 times 2, let's not forget times 2 because it's a two-sided test, and an upper bound of 0.005 times 2. Right? Because once again, let's not forget, this is a two-sided test. Hence, I must multiply my probabilities that I'm getting here by 2, right? So basically, when you multiply these two probabilities here, what it tells me is that the p-value is anywhere between 2 times 0.001. What is that? That's 0.002. Yeah, and 2 times 0.005, which gives me 0.01, right? So the idea is that now I'm looking at a p-value that is anywhere between 0.002 and 0.01. Let's go back to the decision rule. The decision rule here says that you will reject the null hypothesis if your p-value is less than your level of significance. In this case, if you remember correctly, we said that for x2, the p-value was in an interval. We were not able to find an exact p-value, but we said that it lied anywhere between 0.002 and 0.01. Either way, it is less than 0.05, if that is the level of significance that I am using to conduct this test. Hence, here I can reject the null hypothesis. And so very quickly, let's just go back to the Excel output. And here we see that, indeed you do have p-values. The p-values are provided in your statistical package output. So depending, of course, on which independent variable you're testing for, the p-values will be different, right? So here you can see you have a more precise p-value for the variable x2, and you see that in fact it is of this much, and this is indeed less than the level of significance of 0.05. Hence, it confirms again the conclusion that we just drew, which is to reject the null hypothesis. Okay. Here, let's not forget that we have also our confidence intervals for the different betas. So here, this is the confidence interval for beta 1, and this is the confidence interval for beta 2. And it is these confidence intervals, of course, are based on your point estimates. So point estimate for beta 1 is 14.1996. That is obtained through the method of least squares. The point estimate for beta 2 is 22.8107, and so you know, a confidence interval is built based on this point estimate. Okay. So let me just show you very quickly again what um, the formula is for confidence intervals here for your different beta j's. So here we are. This is just a quick refresh on how to come up with a confidence interval for a beta j. Okay, so this is your point estimate, and this is your margin of error. Don't forget, margin of error is always made up of a critical point times your standard error over here. Okay. Now we look at confidence interval and prediction interval. Okay, so the confidence interval for the mean value of y, of course, for a given set of values of x of 1 to x of k, is it follows this form right here, where your y hat over here serves as your point estimate of the mean annual revenues for the example that we're using in this video. So here we have y hat, okay? And that's as a result of course, plugging in the different x1 to x of k different values here in my fitted regression equation, right? And then around that point estimate comes this margin of error. Margin of error here is made up of a critical point, so that's the coming from the t-distribution. For degrees of freedom here, by the way, the degrees of freedom here is always n minus k minus 1. So please note that. The degrees of freedom here is always going to be for n minus k minus 1. Yeah, I should probably add that. And so that is multiplied by a standard error for y hat. Now the standard error for y hat here is the product of the standard error of the model, of the regression model. So that's S, which if you remember is in fact the square root of your MSE. Okay, that's what S is. Times here this added factor here. This factor, which is the distance value time, and taking the square root of that distance value. Okay, so the distance value, let's not forget, is a measure of the distance of, in this case, the combination of values of x of 1 to x of k from the center of the observed data. Okay, so when you're using distance value in multiple regression, it can get a little tricky because here you're dealing with many independent x variables, right? So leave it to the statistical package here to come up with the distance value for you, and life will be easier that way. Okay, so I'm going to discuss that in just a short moment. But before that, I just want to remind you that the farther this combination of x values that you have here is from the center, well, the larger the distance value is, right? And if you have a very large distance value, this means that you will have a longer margin of error in your confidence interval over here, or say in your prediction interval over here, right? Um, the, what I'm saying right now applies to both confidence and prediction intervals, so take note of that. And so if you have a longer margin of error, then you have a longer confidence interval and prediction interval. Okay. And it's also it makes perfect sense because the farther your combination of x values is from the center, well, the more likely you are to be, you know, to be extrapolating, right? You're going away from what you know. So there's more uncertainty attached to extrapolating, right? So that is the idea behind the distance value getting larger as you get further from the center. Okay, and so again, for a prediction interval for an individual value of y this time, well, again, we say that the prediction interval for an individual value of y for a given set of x1 to x of k values is based here on, again, this y hat. Now remember at the beginning we went over this and I showed you how y hat can serve as both a point estimate for mu of y and also as a point prediction for an individual value of y. Okay, this is under the following the assumptions, the four model assumptions, and of course we are assuming that they hold over here, right? So we are using the same y hat here, but this time to build a prediction interval. And where it starts to get different between a confidence interval and a prediction interval is when we look at this, the content in the square root. So here we are taking the distance value plus 1. And this plus 1 will make the prediction interval always wider than a confidence interval. So now I'll discuss very quickly what the distance value is all about. So if you do a little bit of algebraic manipulation over here, you can see that in fact the distance value is really equal to the standard error of your point estimate divided by the standard error of your model, and all of that squared. That is what the distance value is. The problem is we do not know what the standard error of the point estimate is, not easily at least. And so, well, Minitab, so this is where Minitab gets to be pretty handy over here. Minitab actually provides you this distance value, which it calls the standard error fit. Okay, so it's SE fit. That is how you recognize the distance value in Minitab. In order to get this SE fit, of course, you have to feed in some X, you have to feed in the X values. So here it is setting the X values to be X1 equals 47.3 and X2 equals 7. And that will give you a y hat. That's your y hat over here. So that can be your point estimate, or it can be your point prediction. And so around this point estimate or point prediction will be applied the margin of error. The margin of error, of course, will use this distance value, right? This SE fit. And so here you see how you get your confidence interval for y for mu of y for a set of given values x1 and x2. So you see how much is covered in this interval versus the prediction interval for y hat is now, you know, you can see clearly that it is wider. A prediction interval should be wider than a confidence interval. Okay, so that pretty much concludes multiple regression analysis. Thank you for listening.